A 400-meter ship glides past like a floating skyscraper. Now watch a tiny 10-meter boat struggle against the waves. Logic says the small boat should win this race easily. But the giant ship crosses the finish line first, always. There's an invisible speed wall small boats can never break. And it has nothing to do with engine power at all. The wave a boat creates becomes its own prison, forever. One number alone decides how fast any ship can go. That number is length, and it changes everything you assumed. By the end, you'll never look at ships the same way. Picture a massive oil tanker, longer than 3 football fields. Now picture a small fishing boat, barely bigger than a car. Both push through the same ocean, the same water, same rules. Yet the tanker can cruise faster than that little fishing boat. This feels completely backwards to almost everyone watching right now. We're taught that bigger means heavier, and heavier means slower. That rule works for trucks on highways, but not for ships. Water plays by a completely different set of physical rules. Every ship moving through water pushes up its own wave system. Watch closely. A bow wave rises right where the hull cuts. That wave grows bigger and steeper as the ship speeds up. Eventually, the ship gets trapped inside its own wave pattern. It's like trying to run uphill on sand that keeps shifting. No matter how strong the engine, that wall of water fights back. Here's where ship length quietly enters the picture as the hero. A longer hull creates a longer wave before it gets trapped. Longer waves simply travel faster through open water, always true. So a longer ship can chase a faster wave before stalling out. This single relationship explains almost the entire ship's speed mystery. Naval engineers have a name for this hidden speed ceiling. They call it hull speed, and it's calculated with startling simplicity. Multiply 1.34 by the square root of the waterline length in feet. That number gives you the maximum realistic speed in knots. A small 10-foot boat maxes out around 4 knots, roughly walking pace. A 900-foot ocean liner can theoretically reach 40 knots. That's the difference between jogging and flying down a highway. Same water, same physics, wildly different results based on one variable. So why does this matter beyond just satisfying our curiosity? Because it explains why cargo ships, cruise liners, and warships are massive. Size isn't vanity, it's a direct hack against the laws of water. Let's break down exactly why waves control a ship's top speed. As a hull moves, it displaces water at the bow and stern. This creates 2 distinct wave systems traveling along the ship's length. At low speed, these waves are small and mostly harmless ripples. But as speed increases, the wavelength between crests keeps stretching longer. Eventually, the wavelength matches the ship's own physical hull length. At that exact moment, the ship sits trapped between its own crests. The bow rides one crest while the stern sinks into a trough. This creates a dramatic uphill climb that eats enormous amounts of power. Adding more engine power barely helps once this trap fully engages. This is exactly why small speedboats look violent at high throttle. Watch the bow lift dramatically while the hull fights its own wake. Now compare that to a massive container ship at cruising speed. Its wake looks almost calm, barely disturbing the surrounding ocean surface. That calmness is proof it hasn't hit its own hull speed trap yet. There's still enormous room to accelerate before the wave wall closes in. Now let's introduce a second hidden advantage, the square cube law. As a ship's dimensions grow, its volume increases by the cube, but its wetted surface area only increases by the square. That means bigger ships carry more cargo per unit of drag. Friction resistance grows slower than the ship's total carrying capacity. So proportionally, a giant ship fights less drag for its size. This is why massive tankers can be shockingly fuel efficient per ton. Meanwhile, small boats fight a much harsher drag-to-power ratio. Every extra knot costs them disproportionately more engine effort. Now picture the SS United States, launched back in 1952. Nearly 1,000 feet long, powered by 4 massive steam turbines. It crossed the Atlantic Ocean in just 3 days and 10 hours. That record still stands unbroken by any ocean liner today. Its secret wasn't raw power alone, it was that extreme length. That length pushed its hull speed ceiling far beyond smaller rivals. Meanwhile, a small yacht half its size simply cannot physically compete. No amount of horsepower changes the hard ceiling set by length. This is why Formula One boats look nothing like cargo ships. Racing boats plane, literally rising up and skimming across the surface. Planing escapes the wave trap entirely by leaving displacement mode behind. But massive ships can never plane. Their weight makes it impossible. So giant ships must win through length instead, not lightness. Two completely different strategies solving the same physics problem differently. This is also why naval architects obsess over waterline length numbers. Every extra meter of length raises the theoretical speed ceiling slightly. Warship designers stretch hulls specifically to chase higher combat speeds. Destroyers are famously long and narrow for exactly this reason. That slim silhouette isn't style, it's a speed-hacking engineering choice. Meanwhile, stubby, short hulls hit their wave ceiling almost immediately. That's why tugboats look powerful but never move particularly fast. Their short length locks them into a painfully low speed limit. Now here's a fact that surprises almost everyone who hears it. Blue whales, nature's largest animals, are also remarkably fast swimmers. Their enormous length lets them exploit the exact same wave physics. Nature discovered hull speed advantages millions of years before engineers did. Evolution and naval engineering arrived at the exact same solution. Long, streamlined bodies simply move through water more efficiently everywhere. This isn't a coincidence. It's one universal law governing everything wet. So does this mean bigger ships always win every single race? Not exactly, and this is where the story gets more interesting. Modern engineers found a clever way to cheat hull speed entirely. It's called a bulbous bow, that strange bulge below the waterline. That bulb creates its own wave that cancels part of the bow wave. Less wave resistance means the ship can push its ceiling higher. Almost every large modern cargo ship uses this exact hidden trick. Next time you see one, look closely just below the surface. There's also another twist. Not all speed records favor giant size. Hydrofoils and hovercraft lift entirely out of the water instead. By flying above the surface, they escape hull speed limits completely. These specialized vessels trade cargo capacity for pure raw speed. So the real answer depends entirely on what problem you're solving. Need to move thousands of tons across oceans? Length wins every time. Need pure speed with almost no cargo? Lifting out of water wins. This explains why our oceans are filled with such wildly different ships. Each hull shape is a direct answer to a specific physics equation. Nothing about ship design is random or purely aesthetic decoration. Now think back to that opening race between the giant and the tiny boat. The small boat wasn't weak, it was fighting an unbeatable wave trap. The giant ship wasn't lucky, it simply obeyed the length equation perfectly. Physics decided the winner long before either engine even started running. This single insight rewrites how you'll see every ship from now on. Size in water isn't about intimidation, it's about escaping a trap. And that trap is built from nothing but the ship's own wake. Think about how strange that truly is when you stop and consider it. The very water a ship pushes aside becomes its greatest opponent. And the only real weapon against that opponent is raw length. Not horsepower, not steel thickness, not even the shape of the hull alone. Just length, quietly rewriting the rules of speed across every ocean. That's the paradox hiding inside every massive ship you've ever seen. Bigger isn't just impressive, bigger is mathematically, physically faster by design. Once you see this pattern, you cannot unsee it in any harbor. So next time you stand at a harbor watching ships pass by, look at the length first, before you even notice the engines. That single dimension already tells you its true speed potential secretly. Every wave rolling off its hull is riding an invisible speed limit. Nature wrote this rule long before humans ever built a single ship. Blue whales, ocean liners, cargo giants, all obey the exact same math. Water simply does not care how much horsepower you throw at it. It only respects one thing: how long your hull truly is. Now you understand a secret most people never learn in their lifetime. Physics hides in plain sight, inside every wake trailing behind a ship. If this changed how you see the ocean, you're not alone. Drop a comment telling me the biggest ship you've ever seen in person. Was it as fast as this video suggests it should have been? Hit subscribe if you want more hidden physics explained through everyday things. Next time, we're breaking down why airplanes get more efficient the bigger they get. Same hidden math, completely different machine, equally mind-bending once explained. Thank you for watching all the way to this very last second. Every ship you see from now on will look completely different to you. Not just steel and cargo, but a living solution to an ancient equation. The ocean has been running this math experiment for billions of years. Humans just finally learned how to read the answer correctly. See you in the next video, where more hidden truths await discovery. Until then, keep looking closer. The truth is always in the details.